So that's the housekeeping piece that I need to do. So today's topic is community and district systems. Renewable heating and cooling is the focus of what we're looking at with these district systems. And so a little bit about what we're going to try to do today. Obviously, introduction of the topic. Wanting to do introductions of my colleagues in this, and you see the logo there, Geothermal Energy in Illinois, and part of the coalition, and also there's a project grant that pulled this group together. Andy Stumpf and I got together and started a proposal, and then we brought Dr. Tushi Baser and Nancy Odrago on to help facilitate and bring a little more depth to the project we're working on. The project is really looking at providing both a resource going forward in the form of a dashboard for data that's available out there, but also providing education like this webinar for the general public, for people who are either in decision-making modes or in decision positions for communities, homeowners and business owners making decisions, and also for those people who are doing design work and that kind of stuff. So that's a little bit about what got us to this point. As I say, today's webinar, we're really going to talk about a very specific piece of that in the district, that is the community and district systems. Our presenters today, and I will be handing this over to Nancy to talk a little bit about our partnership and some things, and she will be introducing Dr. Baser, and then our main speaker will be presenting right after that. We'll introduce him and get him started. Brian Urlaub, who's Associate Vice President and Director of Geothermal Operations with LaSalle, or with Selene O'Brien. And I realize I just messed that up. I'll let Brian straighten that out. But we are glad to have him available. And with that, I will turn this over to Nancy before I mess up anymore.
Thank you. Great. That's great, Jay. We're very grateful to Brian and to his work with his organization and what he's been doing across the country, and looking forward to his presentation. I just want to take a moment and recognize a network of organizations here that we're also very grateful to. We're grateful to this group of organizations that's shown us support and encouragement of our efforts to increase awareness of geothermal energy across our state in order to assist Illinois' net zero mission and help the transition with workforce capacity and bulking up our renewable energy sector. So this is the Illinois Geothermal Coalition, which is a group based out of campus, but campus here at the University of Illinois, but also includes a lot of other individuals and organizations beyond Illinois, beyond our campus. The Institute for Sustainability, Energy and Environment. This is an institute within the University of Illinois as well that focuses on renewable energy, and so this is a very appropriate topic for them to support with us. The Illinois Water Resources Center, the Geothermal Alliance of Illinois, and the great work that John Freitag does with that group, and the International Ground Source Heat Pump Association, the Geo Exchange Organization, Prairie Rivers Network, Citizens Utility Board, Illinois Clean Jobs Coalition, and the Midwest Building Decarbonization Coalition. These organizations are some of the organizations that work to increase that viability of renewable energy and geothermal as well, and help us with that education just by promoting and supporting and encouraging and beyond. So we're very grateful to them. And if you have an organization that you feel should be on this list, please don't hesitate to contact me, because we'd love to get you into our network and work with you in the future. So thank you again for helping to promote this event. And we look forward to continuing the partnership as we continue to provide technical assistance and outreach in Illinois. Again, I'm very grateful to Brian, but I'm also grateful to the Illinois Extension collaboration grants that were given out to the different teams, and one of those was provided to us to be able to do this work. And so we're so happy to have Andrew Stumpf and Jay Solomon and Dr. Tucci Baser. And I want to now turn it over to Dr. Baser to give us a little bit of information and baseline about this topic before Brian goes in to discuss the more specific topic of district and community scale geothermal energy systems. Thank you, Dr. Bazier. I'm going to turn it over to you now.
Thank you, Nancy, for the nice introduction, and Jay also. So good morning, everyone. Thank you so much for tuning in for this webinar. It's going to be a really good one. This is a part of the webinar series within the context of the extension project that we are working on here all together. So I would like to give you a little bit overview about what we are doing, especially on the Urbana-Champaign campus of University of Illinois, and who we are, and what is our goal, both in terms of research and education. So we, as a group, we are a group of researchers mainly who work on development of geothermal energy system, especially in the Illinois basin, in the state of Illinois, and to promote the installation of geothermal systems, in addition to the enhancement of the design practices. So a group of researchers here have been working really, really hard to understand the subsurface processes and what are those heat transfer, fluid flow, and all those processes, and how they're impacting a design of a geothermal system. When I say geothermal system, I'm mainly focusing on shallow geothermal systems, or you may know it with a low temperature geothermal systems. Here is a timeline, geothermal timeline for the UIUC campus. So it's all started back in 2010. So when it started, I wasn't here. So I joined somewhere in 2018 to the group. But until then, there were various efforts on campus to install geothermal, especially borehole heat exchangers for heating and cooling purposes. After I joined the team here in 2018, we also expanded our collaboration efforts, and also our research efforts on campus especially. So then we were not, and this time we were not just like limited to borehole heat exchangers for ground source heat pumps, but also we also installed energy foundations on a new existing building right now on campus, which is a part of civil engineering building. So you see different various projects, and now you can see the map. So you can see how they're located on our campus. This is the University of Illinois Champaign-Urbana campus, and various projects going on. But I like to emphasize that these projects are individual projects, right? They stand alone, and they represent only one geothermal system installed in a particular building or a greenhouse on campus. So at this point, I would like to initiate our poll, because I'm sure most of you have been familiar with this individual geothermal installation projects, but I would like to kind of like know how many of you are familiar with the district scale or community scale geothermal system, or if you have any experience with it. If you don't mind, I mean, of course, I'm a teacher. I gave you an assignment. I had to prepare you an assignment. So thank you so much for filling the poll. Let's give it a second or two until 80% maybe.
Let me know when you want me to add in the rest of your slide.
Okay. After this poll. All right. Great. So 86%, which is a really good number. Thank you so much for filling this out. Now I can see that 70% of you guys heard about district community scale geothermal system, but very, less than half of you have experience with it. So because this webinar is going to focus on district scale geothermal systems especially. So we would like to provide you more context, but before I hand over to our speaker, I would like to mention a couple of things and why we are considering district scale geothermal systems, especially on our campus. Like I mentioned, so these the projects that are on the campus, they're individual, and there's cost analysis, economic analysis that we performed so far, and also in addition to the environmental impact. But we all aim for increasing the efficiency of installation of these systems and also the operation. These systems have been proven to be more efficient, the most efficient actually when they're at the community scale. So here's a figure on your right-hand side explaining different types of district scale heating and cooling systems. This is not specific to geothermal, just to note. So the first generation was included steam for heating and cooling distribution, and it started in the early 1800s. And it was abandoned because it was not very efficient until the second generation came out, which includes different type of systems, heat storage, industry surplus. So these systems include insulated pipes, but so these systems were not really efficient in terms of they had a really high energy loss during the distribution. So that's why we had to abandon them until the third generation, the prefabricated insulated pipes were started manufacturing. So, and as you can see in this figure, this is where we introduced geothermal systems, and which is in early 1980s. And since then, we've been working really hard to actually enhance these systems and to promote the installation as well. So actually, another reason that I like to emphasize why we abandoned especially second generation system is the oil crisis that we faced back in the day. So considering this is not a political talk, but considering the situation, different events going on, unfortunate events going on in the world right now, we're facing another oil crisis right now because of the disruption in the supply chain. So we would like to overcome these, and we would like to make our renewable energy systems more efficient. So that's why we really need the fourth generation systems, which have the ability to supply low temperature district heating for space heating and domestic hot water especially. And it needs to have the ability to distribute the heat in networks with low grid losses, which is a key point here, because so couple of the reasons that we abandoned previous systems were the high grid losses, and this fourth generation should be able to recycle heat from other resources, such as solar and geothermal. This is where we are expanding geothermal system to be a two-way district heating and cooling system. So to conclude and to sum up here, so many of you, I'm sure, familiar with the individual projects, but we really need to push to prepare to push for the district or community scale geothermal system to make these systems more efficient and to prepare for the impacts of climate change and any supply chain problems that we may face in the near future. Thank you so much for the time given to me to explain this. I'm gonna hand it over to our speaker. Or Nancy.
So Brian, I will quit sharing this. I would remind everyone, as we said before, as Brian starts here, to keep your microphones muted and cameras off, just to save some of the bandwidth for everyone. And at this point, I will let Brian take over.
Yeah, thanks, Jay. Thanks everyone for tuning in, and appreciate Dr. Bosser's talk as well. And I think she explained very well what we're really talking about today, which is the low temperature or shallow geothermal. Just want to make sure nobody's confused that we're not trying to produce electricity here. We're using geothermal for space conditioning, heating and cooling. So what they contacted me and asked me to talk about was the district and community scale geothermal systems. And just a little bit of background about myself. I've been in the geothermal industry since 1997, when I took my first IGSPA course and installed my first geothermal heat pump. Been in the industry ever since, 100% of the time, starting in 2000, worked for a manufacturer of geothermal heat pumps for 16 years. And then now been at SALAS O'Brien for going on 4 years. And SALAS O'Brien is a design consulting firm that designs geothermal systems all over North America. And what I'm going to show today is really two different types of systems. We'll be talking about campus or it could be private or university type campus district systems. And then also some residential multifamily community scale district geothermal systems. So with that, I'll go ahead and get started. So first of all, why do we want to interconnect these systems? And Dr. Bosser actually made a couple of really good points, is that, the efficiency of the system is, obviously a very key component to district systems. One of the other key components to not just efficiency, but also making these more scalable and more cost effective is the diversity that you generally have with a lot of different thermal load profiles, different building use profiles that would be connected into a district type system, especially when we're talking about higher education and campus district systems. We have a lot of diversity on campuses with the student body moving around throughout the day, from the dormitories to the, to the food halls and to classrooms and auditoriums. And then again, with the domestic hot water as well, getting up in the morning, showering, going to class. So there's a lot of hot water demand in the mornings, but not necessarily throughout the day. So you can downsize a lot of your equipment, your ground loop heat exchangers, because of that high diversity, because everything is interconnected. Now, when we talk about residential communities, there might not be as much of a diversity factor as you would see in a typical campus setting, but you still have schedule differences. I mean, obviously, everybody knows no two families live identically, the same. Their schedules are different. When they do laundry, when they get home from work, when they leave for work, those types of things, what they keep their comfort settings at, if they're doing any setback control. So all this goes into play when you look at the aggregate thermal profile that's going to be connected to the system. And that diversity really impacts the total size. And then, of course, the end cost of that community or district system. The other thing that district systems really have, and back to Dr. Bosser's point, is really important. When you have high temperature systems, you lose a lot of heat in the district or distribution piping. The great thing about geothermal, especially the ambient or low temperature geothermal systems, when we're pumping ambient temperature water throughout these districts, we're actually picking up energy versus losing energy. Most of the time, the ground is either going to be cooler. If we're in the cooling mode, we're cooler than what our fluid would be, or if we're in the heating mode, the ground is a little bit warmer than potentially what our fluid would be. So we're actually gaining energy and not losing energy. And when you have a district system, obviously you have a tremendous amount of piping in the ground. All that piping needs to be accounted for because it does have some heat transfer, coefficients. And so anytime you've got pipe in the ground, we should be looking at that. And these district systems really offer a lot more heat exchange through that distribution piping than your smaller scale or one-off buildings or residential homes, if they had their own system. Which in the past, if you were, designing these, one-off systems, you wouldn't take into account any of the lateral or horizontal piping for heat transfer. It was strictly the actual heat exchanger portion itself, whether that be vertical or horizontal, but only that piping was accounted for, not the lateral piping or distribution piping. The third part is really more about the cost benefit of district systems. And it comes down to, if this technology is really going to make it into a mass adoption in our society, how do we get there? And the biggest part of that is ownership, utility model type ownership, which lends itself to district systems. Utilities and third-party owner operators, these companies that will finance, design, build, own, and operate these systems generally aren't interested in, going from homeowner to homeowner or from, building to building. So district systems are really important from a, mass adoption perspective, and really makes it more attractive as a utility model for, some of the utilities to be involved, or, these companies to have, larger systems that they can put in place, and they're guaranteed that they're going to have people connected to and that they have customers. So what are some of the challenges of district systems? Well, obviously the first challenge is overcoming the cost, especially when it comes to residential and community systems, because we've run many projects in cost scenarios, and individual loops per home is certainly more cost effective than a district-wide system. But back to that last point is most, third-party or utility type companies don't want to go in and own individual loops. Plus, you also lose the benefit of all the diversity and lateral piping, heat transfer, et cetera. So, but that cost is certainly a barrier, okay? The other barrier is, especially with, again, the residential community systems, is these larger pump stations that need to move the fluid around the community. Where are those located? There's more energy that's involved to move that fluid. So pump sizing and designing these systems such that you're not using a lot of extra pump energy and parasitic losses in energy just to move the fluid, is really critical to these systems. You obviously have a lot more volume in a fluid, and so you have chemicals and antifreeze in treatment, so that there's a little bit of cost there. And then, of course, where does all this piping reside? Is it in the street, in the right of way? How do you work that through with the city or the regulatory bodies to make sure that this can be accessed if needed? The ownership structure, et cetera. So those are all the things with costs that need to be looked at. The other big one is space. We get into this kind of debate with district systems quite often, especially when we're talking about campuses. Most of the campuses around the country, have been there for a long period of time. They have very limited space. They're putting up new buildings. And so space is a really difficult thing to overcome, because there's not enough green space to handle generally the load that would be needed to heat and cool all of these buildings. So if you're thinking about going in and putting in a heat exchanger for every building, you would need a whole lot more space and have a lot more disruption around campus than you would if you had a couple of common areas and then use the district system in order to do that. And we've got some examples coming up that I think you'll see what I'm talking about. From a residential perspective, the right of way in space for infrastructure, whether it's existing or it's a greenfield site, it's very important to how you're going to get the infrastructure installed. you know, if you're tearing up streets or existing yards, et cetera, to get the piping installed, you know, you've got mature trees, you've got a lot of other utilities also in the street. So the space is always a concern. And again, if you're going to put pump stations in, where do those go? Whose property do they sit on? You know, so those are all things that really need to be, you know, thought about from a high level early on when you're master planning these types of systems, because they can be, you know, roadblocks down the road if they're not, you know, dealt with up front. And then the last thing, especially from the residential, anytime you're in, you know, public property, the, you know, the red tape getting through the city or the city planners, the, you know, working through all that takes a lot of time. There's not a lot of precedence that's already been done in this country for these types of systems, even though there is on the other side of the utility, you know, table. You've got water, sewer, gas, you know, all these things that are already there. But because this isn't technically a utility, or at least not yet, most of these companies are operating as a non-utility. It's more of a service company, even though they might be located within the right-of-ways. You know, there's a lot of new language that needs to be sought, you know, or figured out and worked through with the city and regulators to make this all happen. And so anytime we get involved in these types of projects, if there's any precedent that's out there, boy, if we could share that in the industry, it would be really helpful to show other cities and you know, regulatory agencies that this is how it can be done, because that's going to be, you know, a barrier that's going to take time over the next few years to get through to really have mass adoption of this technology. So let's get into designing these just real quick and from a high level. You know, obviously, any type of system that you're looking at with geothermal, developing the thermal energy profile is first and foremost and the most critical component. And again, it goes back to, you know, the aggregate loads, how much diversity can we, you know, anticipate within the different types of buildings. That's why mixed use system, you know, properties or you know, projects are most appealing, because if we have some buildings that have excess energy and some buildings that need more energy, we can connect those and then share that energy. Whereas if, you know, we're at an industrial site and everybody's trying to get rid of heat, or if we're in a, you know, residential community where everybody needs more heat, especially in the northern climate, you know, that doesn't offset enough of that ground heat exchanger to really make a huge difference in upfront cost and capital investment. But this is really the most important step into developing that you know, designing the system would be developing that thermal profile. And these are just kind of what it looks like, you know. And then, you know, one of the other things to really consider is the domestic hot water, especially when you're in, you know, the more cooling dominant climates, or when you're in the multifamily sector, even in some of the northern climates now with the passive house type buildings and the high energy efficiency of the buildings now. You know, most multifamily buildings are turning to cooling dominant, even in places like New York and Chicago, because of the you know, how well the buildings are being built. So we want to get rid of heat. Let's use that waste heat. Let's use it for domestic hot water. Let's figure out you know, how much of that simultaneous load that we have here, because anytime we have simultaneous load, if you can see on that bottom graph there, that purple area, that basically reduces that ground heat exchanger and that energy that's required to run compressors. And again, depending on the types of systems, if you're talking about a central plant, we don't need to run the ground loop in order to provide energy for that simultaneous load, because our chiller plants can do heating and cooling simultaneously and do that at about double the efficiency. And I'll show you that here in a little bit. But thermal profiles are really important to understand, and doing the best job you can to make sure you've got all the assumptions right so you can design a system effectively. You know, step two is really figuring out you know, what type of heat exchanger works best. And there isn't an answer to that. It's all site specific, really. It varies on how much space do you have, what are the costs in your region to install these different types, what are the soil conditions, you know, do you have any other opportunities for sources like lakes or ponds or rivers? Those are all questions that are very site specific, and you really don't know that until you get into specific projects. But there are a lot of different ways to harness the energy from the earth. And so one isn't necessarily better than the other. It's really just a function of cost versus space and availability. And then the last thing is selecting the distribution or a piping system. And again, this would depend on, number one, is there a potential central plant involved? So is it more of a campus type project? Or if it's a community project, is it more just a pumping system? And are we pumping from a central bore field or well field to all the buildings, or are we going to have distributed well fields? So we might have a 1 pipe or a 2 pipe or potentially even a 4 pipe with a central energy plant. So again, more project specific, but there's a lot of different options. The key here is a couple things to always note. We want to reduce the amount of pump energy as much as possible to make all this happen, because with district systems, largely your efficiency will depend upon how well you design your piping network and your pump energy, because that's where you're going to lose the most of your parasitic losses if you don't do it right. So it's really critical to get this part right. Okay, well, let's get into a couple of project examples. So I'm going to start out first with the district campus conversion. So these are some of the projects that we've worked on over the last, over a decade. And a few of the campuses, higher education, are from fossil fuel conversions and steam to all electric, low temperature hot water systems. And then there's also an ambient system, which is a private corporate campus. And just a little bit of to show you kind of what's happening in the marketplace. The community scale and district scale geothermal is the interest has exploded. These are just the projects that our company is working on and have worked on around the country when it comes to campuses and district type geothermal systems. So as you can see, 10 years ago, there might have been 3 dots on this map. And this is really becoming a popular topic to try to figure out mainly how do you decarbonize, how do you electrify, and how do you meet your climate goals. Most of these universities and corporations have signed on to climate pledges and climate goals. And so in order to meet those goals, they have to do something on their campus that's, other than just replacing equipment like for like, even if it's higher efficiency, to get off a fossil fuel, to decarbonize on site and go electric, geothermal is really the best and most cost-effective option. One thing to keep in mind when you're looking at, especially campuses, but any district system for that matter, really is, what are the different options and sources that you would have to meet those goals? Geothermal is one fantastic source and option, obviously, for heating and cooling and domestic hot water. But there's also, the electric side of it. Once you've decarbonized and gone all electric, well, obviously the grids are all getting much greener these days, but they're still not 100% renewable. So how can we reduce the carbon emissions from the grid perspective? Putting in localized solar panels, PV systems, potential battery storage, sewage heat recovery or waste heat recovery is also becoming a very popular technology that can reuse and recycle waste heat that's already been paid to heat. We're just recapturing that, and we can utilize that right back into and combine it with a low temperature hot water system and or an ambient system. So there's a lot of different technologies that are really emerging into the marketplace that can give you a suite of options to really get to your end goals a lot quicker than there was even 5 years ago. So this is a corporate campus in Verona, Wisconsin. This is the largest geothermal system in North America. This is a private campus. This is a software company. There's about 14 or 15,000 employees on campus. They're building buildings constantly. There's over 40 buildings there now. You can see 8 million square foot of conditioned space, 15,000 tons of cooling capacity. And this is a brand new, this was a greenfield site. These are all newer buildings. This system was started in just over 10 or 12 years ago, was the first phase of the project. And now they're on to their, I think, 4th or 5th phase, but there's a multitude of sources on this campus, which is really interesting. There's 4 bore fields, and the initial couple bore fields were only drilled at 300 feet. And we realized that, you know what, we're going to be running out of space soon if they continue to build more buildings. So we started to go deeper to try to capitalize on more energy per foot, square foot or footprint of the bore fields. So there's, over 5,000-6,000 boreholes there on site. And then we've also got a huge mat slinky loop in a pond that was dug, as you can see from the picture there, and installed. And then there's also an open loop from a quarry that was flooded and utilized as a open loop system to help balance some of the energy. So you can see from this picture here, here's the quarry up on the top right. We've got a couple of bore fields in the green. So these on the bottom of the diagram are the first phases, and then the ones at the top are the later phases. And what we have here is an ambient loop system. So we have a pump station that interconnects all of this. We have a large energy loop that circulates around campus. That pipe is a 36-inch pipe that flows at peak capacity around 80,000 gallons a minute. And that interconnects all of the energy sources and then goes to the main or the central energy plants. And then there's smaller, what we call energy usage loops, where we'll connect 5 or 6 or 8 buildings together with one central energy plant, and then pipe hot and cold water to each of those buildings from that small district plant. And we're using geothermal heat pumps, obviously, in the central energy plant to make all that happen. So this kind of has a, there's 3 different really loops, or what you would want to consider here, energy loops. You've got your ambient loop, and then you've got your central energy and district hot water, chilled water loops. The next project is the Ball State University. Most people have heard of this. This was the first college campus in North America that was converted 100% from steam to geothermal. It's been in operation for a number of years. It's also the largest campus, higher ed campus that had converted. Now, this particular campus was still utilizing coal, and they had one central energy plant with steam distribution to all their buildings, and then a number of buildings obviously had centralized cooling. And so the idea was to eliminate the coal, obviously, and fossil fuel and steam, and go to a low temperature hot water conversion and full chilled water conversions in the buildings for cooling. You're just over 5 million gross square feet of campus, and your EUI currently is at 105 today, where they started at about 175. So the EUI is your energy factor, your KBTUs per square foot per year. That's how these are measured. And 105 for a campus is a fantastic EUI. They've also eliminated 75,000 tons of carbon being emitted into the atmosphere. Just a little bit about this campus real quick. There's 2 central energy plants, one north and one south, and there's 2 bore fields, one north and one south, and then it's interconnected through a hot water, chilled water network for the campus. So again, over 10,000 tons of cooling, 47 buildings. It was originally designed for 150-degree hot water to the buildings, because again, most of these buildings are relatively old. They haven't had a lot of envelope upgrades, et cetera. And the facilities people on a lot of these campuses will never believe that you can take these buildings and heat them with 150 or 140-degree water. They're used to running steam, converting that steam to a minimum of 180-degree water. A lot of them are at 200. So one of the big challenges is getting facility directors and managers on these campuses to start turning their systems down to figure out what is the lowest temperature you can operate at before you start to have comfort complaints. And that's one of the ways you can really figure out then what your design temperature needs to be. And that's exactly what we did here to figure out the 140 was actually the lowest. We designed it for 150 to have a little safety factor, but they operate it right around between 140 and 150. So again, eliminated their steam boiler, reduced their energy costs by $2 million a year, 36,000 tons of coal annually, 3,400 tons of coal ash. All their cooling towers and water use and chemical treatment from the cooling towers are gone. So a ton of benefits to these district systems. But if you were going to go into a campus like this and do one building at a time, first of all, it would take you decades to do that. Second of all, you don't have enough green space to put loop fields everywhere. And the third thing is with these district systems is you get all the diversity of this interconnected system of the student body moving around throughout the day, which is a huge factor in the overall size of the system because you're not sizing for every building peak. And that's really critical to these district systems. So this is what one of the new energy centers looks like. It's pretty much just a building with some chillers in it. And there's an office you can see here. And most of the time, these are dark rooms. There are no lights on. There's nobody in there as far as directors, or steam boiler operators or anything like that. They're self-operating, and you have somebody, basically watching your building automation system and, potentially turning things up and down based on events going around campus and so forth. But overall, they're pretty well unmanned, and that's also where they save a tremendous amount of cost is in their facility management and staffing. These are just a couple of the chillers that are installed there on site. Miami University in Oxford, Ohio is another project that was recently completed. While they're on their fourth phase of completion, there was a total of 4 phases for the entire campus. And their campus is even getting better results than Ball State. And primarily because with this particular system, we went with smaller chillers, more modularized to be able to get better turn down, which increases your overall efficiency of the system. And there's 4 central energy plants here instead of 2. So again, going a little bit smaller, but that was primarily due to just phasing and getting, obviously all this constructed without disrupting the entire campus at one time. You've got about 8 million gross square foot here. And so this is really kind of how it was laid out in the phasing. So you've got kind of the south west campus, northwest, northeast, and then southeast. And so just to talk about the south campus a little bit, that was the first phase that was completed. There's about 8,300 square or lineal feet of hot water, chilled water piping. We had about 690 vertical geoheat exchangers and then a geopond. That geopond is really there and was installed for more of a ballast to pre-cool the ground loop in the spring before the summer season, because the summer season, we just wanted to make, it was a cooling dominant profile. We wanted to make sure we weren't going to overheat the ground loop. And because they had a man-made body of water for water retention, we put a mat loop in the bottom of that pond, and they circulate that. What they found is they were able to circulate that fluid directly to the buildings for about a month every March and get free cooling without running any chillers, because that pond is still very cold when the ice is coming off, that you're able to get passive cooling. So again, just adding to the efficiency and finding different sources and connecting that to your overall district, you can do some, fantastic things to really increase your efficiency. And again, this is just a picture of some of the chillers. And again, this is just a new building. That's again, a dark room, 1 person there, that operates the system. You've got about 2,300 tons of cooling capacity in this one central plant. And as I mentioned before, the chiller efficiency, when you look at these heat pump systems, when you're doing simultaneous heating and cooling. So for instance, at these campuses, in the spring, summer, and fall, when you've got a high demand in domestic hot water every morning, but you're cooling the buildings, you're basically just taking and making chilled water for the campus and then rejecting that heat straight to your domestic hot water and hot water loop. And so it effectively doubles your efficiency because you're doing 2 jobs with 1 lift or 1 compressor, which no other system, is able to do that. In previous systems, what they had before was they had to run a boiler to heat the domestic hot water, and you're running your chiller and your cooling tower to make chilled water. So now we can do that all with 1 system and really increase the efficiency. So that simultaneous load and figuring all that out in your thermal profiles is extremely important with these district systems to really increase your efficiencies. and your savings. So here's a little bit of the metrics with Miami University. 56% carbon reduction since 2008, 52% EUI reduction in the last 10 years, 8.9 million annual utility cost savings per year. In total, in 12 years, they've saved $78 million on this campus. I mean, that is a tremendous story to tell with these types of systems, and how you can really impact not only your costs, but also your carbon reduction and your energy reduction. So just using less energy, obviously, decarbonizing your campus, using very little carbon to make any of this happen. So it's really all electrification and geothermal. So now let's jump into community scale and more residential applications and what this might look like. And I'll share a couple of projects with you that we've been involved with. But first, I'm going to talk a little bit about kind of designing these systems and why you choose maybe one way versus another way. Again, as we talked about with the campus systems, there's really kind of two primary designs of these community systems that at least that would make a lot of sense. There, I'm sure there's other ways you could do it, but from what we've seen, really to keep costs in check, take up as least amount of room as possible with piping and trying to get piping integrated with other infrastructure, whether it's in the right of ways and streets, and then keeping an eye on that pump horsepower, making sure that we're not over designing a system that has so much pump horsepower that we're negating all the efficiencies we've gained by going with geothermal. So the first system here is what we call a two-pipe distribution. So that's where we have a supply and a return throughout the district in every home or building that's connected to that district. Okay. Generally, if you think about in the past, when you would do a one-off building, let's say it's a school, you'd go out into the ball field, you put a ground loop in, a common ground loop, you'd pipe all that into the building, and then you distribute that through all the unitary heat pumps throughout the building. Well, this would be no different other than you've got a common loop field somewhere in the vicinity of the community. You're going to pipe that supply and return throughout the community, and each home would be then your unitary heat pump. The issue there becomes, number one, it gets very difficult to route the piping because you're going to end up, there isn't a community out there that's a square, that you're going to be able to route piping effectively without crossing one another. And then it takes a large pumping station to distribute all that water throughout the development. It's also a little bit more difficult to design in some redundancy and resiliency. And then, where are you going to find a place in an existing neighborhood to put a large common loop field? And then where's this pump house going to go? So those are all things that, need to be considered when looking at these systems. Now, the nice thing about this particular application is that every homeowner, every single connection and heat pump would see the same temperature fluid throughout the year. So everybody's efficiency basically is the same. Whereas when we get to the single pipe, I'll show you that isn't necessarily the case. So this is what a two pipe diagrammatically would look like. You have a common ground heat exchanger somewhere on site. You have a common pump system, and you would pump that on a two pipes network throughout the community. And as you can see, you've got a lot of pipes crossing one another. Okay, so it's very difficult to get all that accomplished. And then it also takes a very large pump to pump that entire district. So you're going to end up losing a lot of, energy efficiency in that parasitic pumping loss. Okay, even if you designed it with as much turn down as you possibly could. But, if you have 100 homes here and all these homes are turning on and off, when you have your shoulder seasons, to ramp that pump down and to be able to still provide flow, and be efficient is a very difficult design. Okay. Whereas if we had more individual circulators or smaller circulators scattered around, it would be easier to do that and to match that load profile with your pump speed and your pump energy. Okay. So what I'm going to talk about is the single pipe distribution. And this lends itself to be a little bit more attractive when it comes to community type systems, because number one, if you're putting it in the street with other utilities, now you're only dealing with one extra pipe. Number two, that pipe becomes smaller because it's not about providing everybody with the exact same temperature. And it's really more about the temperature profile in between every connection and every energy source. It's easier to design around N+1 or resiliency with additional pumping and additional loop fields and energy sources. So there's a lot, it's more flexible in the way to design it for resiliency, okay? The loop fields and the energy sources could be a multitude of different kinds. It can, you could put a vertical loop and a horizontal loop and a lake loop or a pond loop all in different locations and interconnected in a way that still works for the entire system, where that gets much harder with the two pipe. Okay. So just to give you an example, this is what that would look like diagrammatically if you were to do a single pipe. Now, again, I don't know too many communities that are laid out this way, but it just gives you an idea that you can place the energy sources in different places in smaller scale. You can interconnect all the homes, and then you have a couple of smaller pumps to just move the fluid in that single pipe around the community, and then you inject energy or reject energy depending on the season in these strategic locations. Okay, we're still taking in diversity. We're still taking into account all the heat transfer of that pipe, but now we have resiliency because we have more than one location for the ground loops. Let's catastrophic failure doesn't not highly unlikely, but let's just say something were to happen with this loop field. Well, I still have 3 loop fields in operation. If this pump goes down, I still have multiple pump locations. I could even put in some pipes across the district here for bypasses in case a pipe breaks or somebody was digging and hit a pipe. We could also put in energy transfer or heat exchangers to isolate fluid from each home from the ambient system. So there's ways to build in more resiliency with this particular system than there is with the other system. Just checking time here. Okay, so let me show you an example of this exact system here. So this is a project up in outside of Toronto. It was a greenfield site, so these are all new homes. There's 312 homes on this district. It is a single pipe ambient system, so meaning that we're just running the temperature of the ground through these pipes. You can see all these little black dots here. These are the ground loops, the vertical heat exchangers that are spaced in a very strategic manner based on the temperature profile of this single pipe. As each house uses energy for in the heating mode, we're pulling heat off of that single pipe. And from one location to the next, we're trying to maintain a 5-degree or less delta T, which means the homeowner closest, if the water's flowing in a clockwise motion, if the homeowner on the first takeoff of that pipe and the homeowner down on the last before the next injection point, they're only going to see a 5-degree differential, which is negligible when you look at the efficiency profile of a heat pump. They would never notice the difference from one energy bill or utility bill to the next. Be very, very minimal. Okay, so even though they are getting different temperatures, it allows us then to downsize this single pipe, slow the water flow down, which slows the pump sizes down or makes the pump smaller, which uses less energy. So we're not over pumping and using a lot of pump energy and getting parasitic loss there in the system. All right. It also gave us a lot of flexibility in where we could place these and work within the right of way of the street, because that was really critical here, that everything had to be in the right of way. There was no public space for any loop fields or anything of that nature. Everything had to be within the street itself. So that was one of the real challenging parts of the system. Now there's about 2 miles of 6-inch ambient pipe. That ambient pipe picked up about 10% of the overall energy needed in the heating season for this system. So we were able to downsize our vertical heat exchanger by about 10% because we calculated how much energy, even though it's closer to the surface and we're getting, a temperature gradient that's closer to the surface isn't as good as, if you're 20 foot below, but you're still warmer than your temperature flowing through the pipe. So we're absorbing energy. We're not losing energy. Okay. And we had resiliency. We have some bypasses built in for resiliency. If one system were to go down, we can shut it off and run 3 of the other loops independently. So it worked out really well. This is fully constructed, and there's about 100 of the homes are built right now and are being started as we speak. So we're going to get some really good information here over the next year of how well this system is operating. One of the other concerns about these types of systems, as I mentioned earlier, is what I call the lawn ornaments. It's the stuff that has to go in the community to operate all this infrastructure. So all these pumps obviously need some type of an electric connection, which would look similar to like a transformer or something sitting on the ground. Now, this particular site, everything was underground. So all the pumps are in vaults underground, under the street, through, access through a manhole cover. So we had an electrical pedestal that served the pump with electricity. And then we also had 4 water pedestals for 4 of the 15 underground vaults that connected in for water makeup. And we're able to monitor, if there were any potential leaks, that we can monitor and measure how much water is being filled into the system, so they would know if there was any issues happening. But, so you have 15 electrical pedestals and 4 water pedestals that you have to place somewhere in the neighborhood that people are going to see. And so, those are just some of the challenges you have to work through with the builder, the developer, the city, things to keep in mind. And then, of course, if these pumps aren't underground and they're above ground, you're going to have a pump house that you can put all this in, but you would have some type of a structure that you would have to build in order to place all that. This was a project in Fall River, Massachusetts. There were 26 apartment buildings, garden style apartments, and they were all served with baseboard electric heat and, through the wall air conditioners. It was a, early 80s vintage apartment complex. So, not the most efficient, existing. So very difficult to plan and, design a system that you, number one, don't completely renovate all the parking lots, because that was the only place we could put the ground heat exchangers, was in the parking lots. Where are you gonna put people's, to park their cars when they get home if you're doing all this construction? And so there was a lot of logistics that went into this. So what we ended up with was 3 to 4 apartments combined on one central or common loop, and then we would distribute from that one building's pump station out to the other, 2 or 3 buildings. And the reason why we didn't just do one at a time was number one, diversity. Number 2, just routing all the piping and having enough space, and how the parking lot's laid out, and, again, constructability. But so this is kind of a pseudo district system. We've got mini districts, if you will, and interconnected. And they also were doing 100% of the domestic hot water in each of the buildings with geothermal. So to give you a few of the metrics, we went from 43 kBTUs per square foot per year with baseboard heat and basically PTAC or window shakers, to 20 kBTUs per square foot per year with distributed heat pumps in each unit and vertical heat exchangers in the ground. And our, let's see, I gotta move that. I can't see that, sorry. What we have for energy savings or energy comparison, now this isn't cost, this is in BTUs, but you're looking at, 50% roughly, or over 50% compared to the baseline with geothermal over the electric baseboard and the through the wall air conditioners. So that was tremendous savings for this particular project as far as energy is concerned with geothermal. And then, of course, when we look at OpEx and carbon, again, we're really close to 50% total savings. Obviously, heating was very good because you're comparing electric resistance to a heat pump that's got a COP of 3.5 to 4. So you're 400% efficiency right there. And then you've got your air conditioning savings as well. And then you've got your domestic hot water savings. So there was a lot of energy savings and cost savings. And then, of course, your carbon, and again, this takes the carbon all the way back through the power plant. So we looked at the actual grid mix, and there wasn't any natural gas being used on site other than I'm sorry, there wasn't any natural gas on site. There were electric water heating, electric baseboard heating for space conditioning, and then air conditioning. So it was really electric to electric. But this is just what happens when you go from a very low efficiency system to a high efficiency geothermal system in carbon emissions. So all this carbon is associated with is just from the grid. There's nothing on site. This was already an electric, fully electric site. And then here's the economic comparison. You know, obviously that's a big component to this. So you can see the orange here is your capital investment. That's, you know, obviously a lot larger investment with geothermal than to replace a like for like system. But then when you take your energy savings into account, your life cycle cost is much better. Okay. And, you know, you're crossing over your cash flow, you know, curve at about 15 to 18 years is where you're crossing the threshold where you're now seeing a positive cash flow. So, you know, overall from an investor perspective or you know, the complex ownership, this was very attractive, and they could meet their climate goals. All right, the last one I'll talk about here is a project that's just in design. And this is in New York City, or just outside of New York. It's on Long Island. This is the ocean down here on the Rockaways here. This would be the water on the south or the bottom of the map. And this is an interesting development. This is a multifamily and single family development. So kind of more of a mixed use. These buildings in yellow here are all, you know, 4 to 6 story apartment buildings. There's a hotel here, there's a brewery, there's a school, and then you've got a bunch of townhomes and bungalows around the development as well. The hard part about this project, it's going to be phased in 6 phases. So how do we develop and integrate a geothermal district community, not only constructability wise, but looking at it from, you know, an energy perspective, and you know, how would you make this all work? So, you know, we took a look at it and went through the master planning phase and looked at all the energy side of it. And basically what we came up with is, again, another single pipe ambient loop with distributed ground loops around the site to interconnect everything. And again, we're taking in all the domestic hot water load as well, because there's a lot of diversity, especially when you get into the multifamily buildings and the hotel, that we can take a lot more diversity in that domestic hot water. And we can also recapture a lot of that energy with sewage heat recovery and inject that back into our ambient loop as another energy source. So those were really critical things to look at when we did our aggregate profile and determine, you know, what does that look like? How much energy do we need? Where do we need it? And what kind of diversity can we take into account? So this is what we ended up with. The different colors really represent the different phasing of the project, but what you can end up seeing when they're completely done is that we'll have a single pipe ambient that runs around the entire development. Okay, we'll have multiple pump stations. So that'll be phased in as it builds out. Okay, and then we have multiple energy sources. So we have, for the first phase here, this bore field and this bore field after we get the pipe extended across the street, which will then handle all these bungalows and these multifamily buildings on both sides of the road here, the hotel, the brewery, and then of course the multifamily buildings. And then when we get onto this side of the street on the right, then we've got the other multifamily buildings, and then lastly, all the other townhomes and bungalows. So you've got a lot of diversity here, but the constructability and phasing was a really key component to figuring out, you know, how can this work? And a single pipe makes this much easier, because now I can distribute my energy sources. I don't have to figure out and put them all in one location and then pipe 2 pipes around this development to every building, which would be a piping nightmare. And constructability, you know, side of that would be just extremely difficult, where this gets to be a little bit more or easier to construct. And the biggest thing is, you know, we just have to find places where they can put these small pump houses versus putting them underground. You could certainly put them underground, but they're opting to put them above ground because resiliency, this is the ocean, hurricanes, etc. They're going to want to try to get this as flood proof as possible. including backup generation to operate the pumps and keep everything going. So just a little bit from an energy side, here's what this entire site looked like when we compiled all the data from the aggregate loads, all the different building types. And in the end, our total HVAC savings with geothermal was 61%. When we add in the sewage heat recovery, we're at almost 70%. With a total savings of 44%. There was some additional upgrades in lighting and so forth that was taken into account. Or I'm sorry, not lighting, domestic hot water. And then from an emissions perspective, again, very similar story to tell. We've got 46% and 41% reduction in overall carbon with geothermal over the all-electric baseline and air source heat pump. This all-electric second column here is an air source heat pump system. So those were our 4 comparisons, and as you can see, geothermal wins out by a large margin. The last thing that they wanted me to talk about was a couple of things. Number one, just to touch on jobs. Geothermal offers, really more jobs than just your traditional HVAC systems. Nothing really changes from a jobs perspective inside the building. Whether you've got a conventional, HVAC system or geothermal, that work is roughly the same. It's all this outside work that adds jobs, for our technology. And really what we're looking at is more of an energy transition or a job transition. We're taking, and hopefully taking in the future, because we're going to need a lot more capacity in drilling and pipe fitting and installation of pipe. So hopefully that oil and gas industry, which we're already seeing a number of, those organizations reaching out and looking into this technology as a transition for them to, instead of drilling for oil and gas, drilling for thermal energy. And so, there's definitely a transition there, but a lot, every geothermal project has domestic jobs right there in the backyard. You're drilling localized, thermal energy systems on site. And then of course, all these district systems, you've got a tremendous amount of piping going in the ground. So the pipe fitters and the pipe unions and all the people involved in putting the pipe in the ground, again, is either transitioning maybe out from the gas utility to now a thermal energy utility, or whatever you want to call it. And then, even on the private side, universities and other private campuses, you've got all that piping networks that need to be installed. And then from the manufacturing side, geothermal heat pumps are built here in America. The plastic pipe is all built here. A lot of it's built here, manufactured here. So, this is really an excellent opportunity to have job growth and transition jobs from sectors that are maybe, regulation is moving away from and pushing towards the renewable, and this is the way to do that. So I think that's really a key thing for our industry to not lose sight of, that we really increase, and have domestic jobs for every one of these projects right here in our own backyard. Let's see what happened. Okay, and the last thing, just to talk a little bit about resources. If you're interested in this technology, if you're interested in learning more about it, there's a lot of opportunities out there and resources out there. The International Ground Source Heat Pump is, obviously the our national organization that really helps with training, with some research. We help develop standards. We work with a lot of the other organizations like ANSI and CSA to develop standards. We work with the Plastic Pipe Institute at IGSPA. So I'm actually on the board of directors of IGSPA. And so there's a lot of really great work going on there. There's also a lot of education and training associated with that organization that they provide. They also work with the American Energy Engineers, AEE, and the Certified Geothermal Designer course. So the course is through IGSPA, but certified through AEE. And so if you're a designer and you're interested in learning more and becoming certified as a geothermal design engineer, that's a fantastic course. I would highly recommend that. ASHRAE is also another organization that often publishes papers and does research about geothermal systems. There's a couple of great handbooks out there at the ASHRAE bookstore that are about geothermal design. And you've got the Plastic Pipe Institute that really has a lot of great information about all this plastic pipe that we're using, and the the heat fusion joining methods that are used to connect plastic pipe, because that's the one great thing about geothermal, that most of this piping that's going in the ground, almost all of it, unless maybe some of these big district systems may get into a little bit of carbon steel or something, but primarily it's all high density polyethylene. Everything is heat fused. So you're talking about, an 80-year asset, according to gas utilities, according to water utilities. They're using the same materials, they're putting the same pipe in the ground, and they classify that as an 80-year asset. Theoretical life is 150 plus years. Basically, the bottom line is you're putting in a system that's there for the life of the building, plus probably more than that, but certainly for the life of the building. So this is a very robust system that's being installed, and doesn't need to be replaced, like other technologies do over time. So these are some great resources. Check them out if you have any other interest in this technology. And with that, I think we're going to go ahead and take some questions through the chat line. So Jay, take it away.
All right. We've got a few questions, and I made the mistake of actually losing some of those. One of the things, do we want to, I think some of these have been answered. There was a question, on one of the last examples there, about the waterway that was used as part of that project. Was that a public waterway or on the
Trying to think of which one we were talking about. What
the
in New York?
The one probably was.
Yeah, there wasn't. We weren't using the waterway there. That was just the site's located next to the water, but we were not using the water. Primarily just regulation to pull and dump back into the ocean, and didn't feel that the developer didn't feel they wanted to go down that route, trying to get that permitted and construct that. So that's all 100% vertical ground loop heat exchanger on that particular site.
Okay. We did have a question early on, and I think we got it answered, that it was, the technology is relevant for rural and small communities as well as large communities. So hopefully we got that one. You want the ability to grow it and expand it, which
that is one of the fantastic things about this technology. When these district systems, they're certainly scalable. You can do anything from 10 houses to 300 houses to 500 houses. I mean, it can continue to grow. And same thing with campuses and whether it's or downtown districts. There's a great little system in West Union, Iowa, that's got connections up to 50 some buildings from a district downtown network. And so it's definitely scalable. It's really just more about the planning, and then looking at how all the energy use is going to happen within the district. So
right. I think you kind of hit upon this, is what's the design life of one of these typical systems if it's adopted, and I think that follows.
Yeah, well, the pipe in the ground is their theoretical life is well over 100, 150 years. A lot of the utility asset publishings are around 80 years for the assets of plastic pipe in the ground, without having to replace it. So, then the inside the building mechanical equipment isn't a whole lot different than your, traditional equipment. However, because they're running at much better and lower temperatures, and they're indoors, you really don't have anything outdoors with geothermal. That's one of the huge benefits, is that it's not exposed to the outdoor elements, that you're going to generally see about a 10-year additional life expectancy on that equipment versus a traditional system.
Here's a related question that just came in. What refrigerant is used? How do you prevent catastrophic loss of large quantities in case of a pipe failure? New refrigerants with less.
Yeah. Well, that's a great question. And actually, these systems are all waterborne. So there is no refrigerant in the actual network of piping. The only refrigerant is in the heat pump itself. And that's the other great benefit of these systems. Even like you look at Ball State, for instance, the project I mentioned, those 2,500 ton chillers, comparative to other systems, they have very small amounts of refrigerant comparative to other types of systems, especially when you look at anything that's got any field piping from a condenser on a roof or outside to the chiller itself. So you have basically a split system where you've got refrigerant lines running outside to inside. You've got a lot more refrigerant in those systems. The VRF technologies have a lot more refrigerant in them than your unitary or isolated heat pumps that are much smaller scale refrigerant. So, and then we can modularize those chillers and not have them so large if there's certain requirements for, you know, if you get over a certain amount, you have to have, you know, somebody there 24/7 to monitor it, or you have to put in all the monitoring equipment. We can design systems that don't have that large of refrigerant volume in one potential leak source that eliminates all that risk and eliminates all that extra cost for facility managers or, you know, mitigation systems and leak detection systems.
I see that Nancy has started our knowledge gain. Had one other, what was the Miami install cost to get the 78 million in savings?
That's a good
Yep.
question, you know, and I actually don't have that. Unfortunately, don't have that cost. I can certainly get that if somebody would like to give you their email or something. We could certainly get that for them.
Okay.
The facilities manager that was primarily involved with that full transition now works for our company, and so he's very intricate knowledge of the costs, everything associated with that, the operation. So yeah, we can certainly get all that information.
Oh, I missed one early on here. And this is probably important to make sure everybody understands. Can you explain grid loss? Started right there in the early part of your presentation. I should have caught you on that one.
Yeah, grid loss. Are we talking about carbon grid loss, or I guess I'm not quite sure.
I think this refers to when you were first talking about grid loss as far as the whole system across the
That
system.
question was asked while actually Dr. Bazer was
okay.
giving her
Oh.
overview. Mhm.
Yeah, so if I already answered Melissa's question, but just to, you know, for the other folks, so grid loss is any kind of energy loss during the distribution of the energy from source to the end user.
Okay. Let me sort through the other questions here, but I know we need to let, since we're going a little over time, why don't we let Andrew provide a little bit of one of the other questions that I kind of suspect is coming up here, and that is funding opportunities out there for these communities. So let me move this and share my screen back. So that he can talk about that piece of it.
Thanks, Jay. Just very briefly here, just wanted to talk about the couple of funding opportunities related to community or district geothermal systems. I put the long URLs in the chat box there. Let me just change that to everybody. Just wanted to note that DOE will soon release a funding opportunity for community geothermal projects. They're going to release $13 million to support projects across the country. And then you can go to the URL and get more information on the notice of intent to fund, but they haven't actually released the funding opportunity announcement yet. And then one program that came out just last week was this $500 million to transform mines to new clean energy hubs. So this is a request for information, but they suggest there'll be a funding opportunity call sometime in early 2023 And just wanted to note that Southern Illinois and Southern Indiana are part of what they call energy communities. And so these are targeted areas of transition of workforces from mining and oil and gas to other industries. So this area of the Midwest would be a focus of possibly some of this funding in geothermal energy as part of some of the clean energy technologies that they're wanting to target. So a district system based on a existing power plant or mine site would be applicable in this funding opportunity. So that's all for me. Thanks, Jay.
Okay, thank you. And we appreciate everybody participating here, and I will go back to some of the questions here. And would welcome my colleagues to see if there was anything I missed. One that was shared around was, and it was more of a question, more of a comment. Any fellow local government entities have existing language / text amendments for code referencing geothermal as a utility, would be interested in. I know that there's a couple of others that were interested in that way. That may be something that we may try to work on. Nancy's team may be interested in trying to work with us to move forward with, but I would say that if you got any of those ideas, would welcome you to share it both with the person who asked with Lauren from the city of Carbondale, but we within Extension would be interested in that as well to help with that. So Kevin asked a question here for the cooling dominant systems. How do you tackle the thermal imbalances? Hybrid systems? The question is hybrid systems, deeper bore. Are there other opportunities for district?
Well, the first and best opportunity is to try to take that waste heat and use it for something else rather than putting it in the ground. So try to combine that with domestic hot water. If you have any other opportunities to heat, to heat something, whether, maybe it's a large pool or it's, it could be a couple of different things. Also, sewage heat recovery can also be used as a heat rejection source. Heating the wastewater, up 10 degrees or 5 degrees is not an issue. So when that water is coming down the drain at 70, to heat it to 75 can certainly be done. So incorporating some technologies like that certainly help. But if you don't have any of those opportunities, it really either becomes a hybrid system where we use some type of a fluid cooler or cooling tower to either, and you can design that a couple different ways, again, depending on where you're located. But what we always try to do is downsize that and use it more of a pre-cooling device. So we're doing it either at night when the ambient is cooler than the ground, and we'll try to take as much heat out as we can, or do it in the spring to try to get the ground back to its natural temperature versus letting it build up year over year. Or you can strictly size it as a peaking system, and just when you hit a certain temperature, now you turn that device on and you're in your peak shaving. So you can do it a couple different ways. If you don't have that opportunity, they don't want to see anything outdoors, then yes, then you have to size the ground loop accordingly, which means more ground loop, more spacing, probably deeper. It just takes more ground heat exchanger to dissipate that heat, so it doesn't overheat over time. Put it in a different shape. Don't put it in a square, something that doesn't going to allow the heat to build up internally.
One question here. How are you estimating the capacity of your horizontal infrastructure? I think that deals with that added efficiency you get into.
Well, I would tell you that we do it longhand, but we don't. We use, in all of our district systems, we use a software called Transys. And Transys is a really highly intricate thermal modeling program that's, takes thousands of different inputs and actually runs simulations. So you can put and build the actual system put all the temperature profiles in and what depth the pipe is at, the size, the flow rate, the, you know, your heat transfer coefficient through that pipe, the temperatures, you know, of the fluid versus the ground. And so we're modeling basically all of that, as well as our ground loops, and then, you know, putting in all of our building thermal profiles to really look at the entire system as a whole. I mean, that's really the critical part. A lot of the ground loop software out there is great for one-off buildings where you're sizing just a ground loop and you're not taking any lateral piping into the equation. But when you have district systems, you have a lot of pipe in the ground horizontally or laterally that really need to be part of the equation. So we look to a different program that really takes all that into account.
All right, here's a loaded one, and actually one that I kind of had an interest in as well. The resilience of these systems seems high. What is the typical rebound time if a large scale system were to be hit by a tornado or power outage in freezing temperatures like what happened in Texas?
Well, that's a really great question. You know, when you're talking about storms, it's, you know, everything is going to be predicated, number one, on what's above ground and did it get destroyed or not. So as much, you know, obviously the ground loop itself and all the piping is below ground. So unless it was a, you know, a hurricane that eroded, maybe if you were near the ocean and it eroded a bunch of the soil and you had exposed piping or piping breaks or something like that. But otherwise, generally, you know, all your piping is protected. Then it's really about the electric grid and whether or not you have backup source to operate the system. But you wouldn't only have to have backup to operate the district, you'd also have to have backups to operate all the individual heat pumps if it's a residential community at every home. So, you know, the electric grid is still the weak link here. You know, we're designing on the New York project to have backup generation available for all the pump houses, but the buildings would still need all their own individual backup as well. But that's what they're trying to design for, is another super storm Sandy, you know, so you have a resilient network underground that's all protected. Now it's really about getting your infrastructure, your electric infrastructure, you know, fully redundant.
Thank you. And I think it kind of leads a little bit to this kind of a question of how's the varying life of various components accounted for in a 25-year LCCA through a residual value or salvage value at 25 years?
Yeah, unfortunately, a lot of the analysis did not take into consideration salvage value, which they should, but they don't. Salvage value is you know, really a key component to geothermal, because there's a lot of salvage value to that ground loop. That ground loop does not need to be replaced after the 25 or 30 years. It's actually now appreciated versus depreciated, because now the cost 25 years from now, what that would be to install and the energy that it provides, the salvage value is much greater than if you had a conventional system. All that equipment gets taken to the scrap yard, and whatever you get for scrap money is all you get. So, you know, you have to decipher the difference between, you know, the ground loop, obviously your energy source, and then the energy or the mechanical equipment. Most of the time in all of our LCCA analysis, we're only taking into account mechanical equipment life cycle and, you know, the extension that you get from a geothermal system of 10 years over a conventional. And that's really it, no salvage value.
Right.
But that's really not correct.
One here is a question that's kind of roll it out to you and to my colleagues. A question you may know the answer to, may not. Can ARPA funds be utilized when making these infrastructure choices to utilize geothermal technology? Is that one we need to investigate?
Yeah, I don't know that I know that answer. I'm not sure if Andrew has I'm not sure what's ARPA. Does anybody know?
That would be the American Rescue Plan Act funds.
Gotcha.
That cover some of the revenue loss, as well as water infrastructure, broadband infrastructure. I do see some examples online where people were granted were given using funds for energy sector infrastructure. So I'm hoping, I don't want to say for sure, but I'm thinking that with some of the leniency, or I guess the allowances of usage for those funds, that it would be able to be justified. I'm hoping that we can even provide a webinar on the reporting requirements and the auditing preparation for ARPA. We have a past webinar that we did on allowable uses of ARPA, and it is very general. So I would retain some hope that, yes, Belinda, that ARPA could be utilized in that way.
Just another note on funding, obviously public funding and, those funding assets are low interest or, excellent if you can get them. But if you can't, there is a tremendous amount of private funding in the marketplace for renewable projects. I mean, I've never seen the billions of dollars that are available as I've seen today for renewable energy projects. That there's all kinds of investor groups, hedge fund managers that manage billions of dollars that are looking to invest in renewable energy projects. And a lot of these geothermal type projects are right up their alley, especially residentially, if there's any type of an HOA or a homeowners association that they can leverage, because HOAs have fantastic credit scores and ratings, and that they can leverage towards the HOA and have a contract with them. Or if it's a multifamily building, like a condo building or something like that, it works really well. But anyway, there's a lot of companies out there that are interested in financing projects. And so if the public financing isn't available, there's still certainly, granted, a little higher interest rates, they're obviously looking for a return on their investment. So your cost of capital is a little more, but there's a lot of money for funding available.
Okay.
Yeah, I was just going to mention the state of Colorado has used ARPA funds are going to use ARPA funds to have a grant, to make a grant program for geothermal energy installations. So I think that's going to be allowable under those funds.
I think we got most of the questions answered. I'm not, oh, here's one. Please tell us how well a mix of new building and tie-ins to existing buildings can work. How amenable is the technology? Is this technology, or how is this technology blend with existing building technologies?
Yeah, that's a good question, because there's a number of pilot projects going on in the Northeast that site selection is a critical step, and part of that is the existing stock of housing and buildings and what type of systems that they have and how well it integrates to geothermal. And so that's a really key step in this process, because a lot of the older communities, and especially in residential, where a lot of the homes are either on hot water heat, and boilers with hot water heat, those systems just don't integrate with geothermal very well. So that means a higher capital cost to retrofit those buildings, because you're basically taking those systems completely out and putting in an entire new system. Versus, you get into some newer communities, 80s on up, where everybody was transitioned to a forced air furnace. With ductwork, those systems integrate, much easier, very, very simple, just taking out the furnace and putting in the heat pump generally, unless the ductwork is really messed up. But I mean, if it's overall that the technology, is a like for like technology as far as the distribution system within the dwelling. So, that integrates very well. And of course, commercial buildings usually can be retrofitted pretty simply, without a lot of renovation, other than just swapping out equipment like for like, if it's rooftop equipment or if it's chillers and boilers or The biggest thing is when you get into high temperature hot water, that does not lend itself with geothermal. So you have to get to a low temperature hot water system in order for it to work. And with residential, there just isn't a lot of opportunity there.
Okay, thank you very much. I think we got, well, I guess there's one come in here. We'd be curious to hear more about how a HOA or a neighborhood community group would need to work with the city and state to make residential projects happen. But I think that's as they say, can be a follow-up for later. I think
Yeah.
that's the next step we're actually so
Yeah.
much kind of thinking about. So
I don't know the specific language. I just know that from a funding perspective, dealing with one client and a group combined in an HOA versus individual owners is much more attractive for a lot of the funding mechanisms. So,
Brian, I would like to
Yeah.
thank you. I know we've gone considerably over
Yeah,
time
thank you.
here but I think we covered some great questions. And I think that the fact that we've got 75 participants or 74 participants still online with us speaks well to it. I hope we've addressed a lot of the questions and provided information to this group. If there's a particular question in here that I've missed in here, feel free to unmute and let me know or ask the question now. Otherwise, we will see everyone. Thank everyone for attending and see you at the next one then.
Yeah, I have a question on whether we can get access to Brian's slides.
Yes, we will be sending, if you're registered for the
Yes.
conference, registered for the webinar, we will be sending out a PDF of the files or a PDF of the slides.
Thank you.
And that will be a few days. It may, and I don't know what Nancy's timeline is on that. A lot of times we try to get the video posted, so we send it all out together. So with that,
Yep. Thank you very much.
thank you very much and have a
Have
good
a
day.
good day. Thank you.